Hi everyone, my name is Neha Kadam and this is lecture 20, and today we are going to learn about stepper motors. Stepper motors, they are precise electromechanical devices used for converting electrical pulses into mechanical motion. Unlike traditional motors, stepper motors move in precise increments or steps, making them ideal for applications which require precise positioning and control. So we already learned about stepper motor in previous lectures, and now we are going to get in more detail about the control mechanism of stepper motors in this lecture. So first is the stepper motor control circuits, and in this we have three important components. This is the first is the controller, second is the pulse sequence generator, and the third is the drivers amplifiers. Now let's break it down. So this controller, it acts as a brain of the system. It determines the number of steps required and the direction of movement based on the specific application demands. For example, in either in clockwise or anti-clockwise. Next, we have the pulse sequence generator, which translates the commands from the controller into precise voltages applied to the stepper motor coils. You can think it of as a as the translator between the digital instructors and motor's physical movements. And then we have this drivers amplifier. These amplifiers boost the power of the signals sent to the motor coils. It ensures smooth and efficient operation. And interestingly, due to the binary nature of the stepper motor, where field poles are either on or off, we can use highly efficient Class C driver amplifiers. And one of the remarkable advantages of the stepper motor lies in their compatibility with digital control. So unlike some other motor types, stepper motor, it requires no digital to analog conversion. And this inherent digital nature simplifies the control process and also overall increases the efficiency. Now let's moving on to the next slide. So in this we will dive into the complete interface circuit of the two-phase stepper motor, and in this we can see this circuit has up and down counter and 2 to 4 decoder. So together they generate the crucial timing waveform which is necessary for controlling the stepper motor's movement. The up and down counter, it is a 2-bit counter, meaning it can hold 4 possible states, which is 0, 0, 0, 1, 1, 0, and 1, 1. And each state corresponding to a particular output from the 2 to 4 decoder, as you can see here. This decoder, it maps the counter state to the 4 distinct outputs. It ensures that only one output is active at any given time. Now let's focus on the output of the decoder. So when the counter counts up, typically in response to counter clockwise pulse from the controller, this output serves as the basis for the driving motor coils. Now to translate these timing signals into the motor coil, into the motor coil activations, we use power amplifiers. So we use power amplifiers, and this circuit, it consists of 4 complementary symmetry drivers, each responsible for controlling one end of each motor coil. Now let's see how this actually works. So when Q1 and this Q4 are activated, then current flows through the motor coil, this motor coil in one direction as indicated from left to the right. And conversely, activating Q3, this Q3 and Q2 in the reverse polarity, causing the current to flow in the opposite direction through the motor coil, right to left. So this was left to right, and then it causes the Q3 and Q2 causes it to flow the current from right to left. And when both Q1 and Q3, if these two are off, then no current flows through the motor coil. There will be no current in the motor coil. Effectively, it will just halt the movement. So it's worth noting that the role of the resistor and here these Zener diodes, this resistor and here these Zener diodes in the circuit, these components they basically ensure that when one transistor is on, the other is off, preventing any potential conflicts and ensuring like smooth operation of the motor. Now, as we move forward, we'll explore further nuances of this circuit, and let's see the next. Okay, so in this we have controlling the 4-phase stepper motor, which is a very important circuit in many precision applications. So at the core of this control mechanism are the outputs of the decoder, as you can see over here, which are meticulously connected to 4 Darlington driver transistors. So you can see this 4 the pair of circuit transistors that you see, they form 4 Darlington driver transistors, and these transistors play a crucial role in energizing the motor coils in sync with the timing signals, this A, B, C, D, as you can see here. Now, as these timing signals go high in the sequence, corresponding transistor are basically turned on, and it effectively energizes the specific coil in the motor. For example, if A is energized, then as you can see in this position 1, we see the positive spike in the timing diagram. Now, what makes these amplifiers particularly noteworthy is that their capability to supply up to 1.5 ampere of current, and which makes them suitable for a wide range of stepper motor application. And also they can be seamlessly driven directly from the TTL 5 volts logic circuit. And it's essential to highlight in this circuit is that the inclusion of these diodes that you see corresponding to the motor to the coil, this motor coil, it serves basically these diodes, they serve as an escape path for the coil, for the current in the coil when the transistor is turned off, and this diode ensures smooth operation and protects the circuit from any potential damage. Now moving forward, you see here is the UCN584B, a sophisticated combination of timing logic and power drivers. So all neatly packed into a single IC, and this integrated this integrated circuit basically streamlines the motor control process. It offers convenience and efficiency in the stepper motor applications. Now let's break it down into basic inputs and operations of this versatile IC. So the primary input are the step inputs in at pin 11 that you can see here. This is the step input, and the direction input 14. This is the 14 pin. The motor's movement is synchronized with the step input, where each pulse applied to this pin cause the motor to advance in one step. Meanwhile, the logic level on the direction pin determines whether the rotation will be clockwise or is it going to be anti-clockwise. And the output transistors, as you can see, these are the output transistors. So these output transistors, they are basically common emitter arrangement, also known as open collector, and this configuration simplifies the circuit design and also offers flexibility in connecting external components. And to the motor coils, we simply attach attach them between the output pins and the supply input voltage. So these are our motor coils in between the output and the supply input. So when output transistor is activated, it completes the circuit by providing a path to the ground for the motor coil current, and thereby it drives the motor's movement. So this circuit that you see here, it basically encapsulates the important components that are needed for precise control of unipolar stepper motors. And this integration of timing logic and the power drives makes it a very important tool in various automation and robotics applications. Now next we have the three operating modes of UCN 584B. The first is the wave drive mode, and in the wave drive mode only one coil is energized uh, uh, at a time, and each step corresponding to toggling between energizing the coils alternately. And wave drive mode, it also offers highest resolution, but it sacrifices the torque compared to other two modes. In the second mode, which is the two-phase drive sequence mode, and this is also sometimes called full step mode. In this, it energizes both coils of the stepper motor simultaneously. As you can see, these two. Each step corresponds to a transition from one coil pair to the next adjacent pair, and in this full step mode, this type of mode offers high torque but lower resolution compared to the other two. Now finally we have the half step mode, and in this mode it alternates between the energizing one coil and then two coils. As you can see right now, it is at a one position energizing this coil, and when it is at this position or either at this position, then it will be energizing the two coils. So as a result, each step is half the angle of the full step, providing higher resolution. So half step mode balances torque and resolutions, making it more suitable for application where we require precision and smooth motion. So these modes that we saw, these operating modes, they offer flexibility to tailor the stepper motor's performance to a specific requirements of the application, whether if we want to maximize the torque, resolution, or a balance of both. So this UCN 584B, it provides the versatility needed for efficient stepper motor control. Now, next is the microstepping. So this microstepping involves driving the adjacent poles of a stepper motor with different voltage levels, allowing for a very finer increment of moments, as you can see, moments compared to traditional full steps. One method to achieve these different voltages is through pulse width modulation, providing a flexible and efficient means of synthesis. And the most common used microstep increment include 1 by 5, 1 by 10, 1 by 16, and 1 by 125, and 1 by 250 of a full step. And this offers a wide range of resolutions to suit various applications. For example, in let's say in microstepping scenario where pole 1, let's say this pole 1 with 3 volts and pole 2 with 2 volts is there, then the rotor aligns itself approximately 3/5. As you can see, this is the 3/5 step of the way to pole 1, resulting in 5 volts microsteps between each regular steps. And it's important to note a couple of key points about this micro stepping. First is that it doesn't necessarily require special stepper motor, but rather a specialized motor circuitry, control circuitry, making it versatile options for enhancing motor performance. And second important point is that the actual position of the rotor in a microstepping system can highly dependent on the load torque. So in this a careful consideration is basically made to the design and operation. Uh, and here, one significant benefit of microstepping, particularly for delicate systems, is its ability to reduce the vibrational shock often associated with taking a full step. So, when the motor takes a full step, then there is a vibration shock you might see when you would have used the motors in your laboratory experiments. But with the stepper motor, with you will see the smoother motion that you will see because of this tiny micro steps, which overall contributes to improve precision and overall system stability. Now, next is improving torque at a higher stepping rates. So, in this, it is important that the stepper motor develops sufficient torque with each step to effectively drive the load. And if the motor fails to do so, then it may stall, as we discussed earlier. Uh, and if it stalls, then it will result in missing the step. And this is a problematic because this is very problematic because when steps are missed, the control loses track of the load and load exact position, and potentially it can what it will do, it will render the system uselessly. So it's important to remember that motor torque is directly proportional to motor current. Motor torque is directly proportional to the motor current, and however, there is a change we face as the stepping rate increases and the average current decreases, and this presents it basically presents a dilemma as the lower current translates to reduced torque, especially at a higher speed. And now let's move forward to the next. So that the challenge that we discussed in the last slide, we face in the stepper control movement uh, is basically a limitation posed by the circuit time constant curve. And here you see the LR drive circuit constant curve here. So the time constant dictates the rate of change of current in the motor winding as we increase the step rate. And there is insufficient time for current to build up the rated value, leading to the reduced torque output. So in that case, the one solution to address this challenge is by increasing the value of the resistance. So you see this resistance. So increasing the value of the resistance in the circuit, we achieve this by incorporating this ballast resistors, which are external resistors added in series with the motor coil. But why do we aim for a lower time constant? It's a very important question to consider. So the answer to that is the electrical time constant basically represents the time it takes for the current in the winding to reach 63% of its rated value, and this value is derived from the system step response, where 1 minus 1 to the power epsilon signifies the time constant. And a lower time constant indicates that current flows more quickly into the windings, and which will enable the motor to reach its rated torque faster. Now let's discuss the role of ballastic resistor in the LR drive circuit. And so these resistors not only improve the torque output at higher stepping rates, but also it limits the current, which may be crucial in certain applications. So the addition of ballastic resistor transformed the stepper motor drive circuits into a LR drive configuration. Now we will see the next solution, which is bi-level drive method. So this bi-level drive method is quite straightforward. So in stepper motor, they are essentially inductors to the drive circuits, and the torque they provide depends on the current flowing through the coils. However, the rate at which the current can increase in proportional to the applied voltage. Now, here is the dilemma. So driving a stepper motor at low voltage and low frequency works fine, and you'll get adequate torque because the rise time of the current is a small fraction of the total step. However, as you increase the step rate, there's less time for the current to rise, which leads to a significant drop in the torque. Now, increasing the voltage might seem like a solution, but it comes with drawbacks. So, overdriving the coils can lead to overheating and require a large power source. Now, in that case, what is the solution? The solution is to use the bi-level drive. So this method uses a two-level power supply. As you can see, the 12 volts and the 25 volts connected to the stepper motor. So when the stepper motor operates at low speed or during holding, it's supplied with a lower voltage. For example, it is supplied with a 12 volts lower voltage. However, when a step is initiated, the switch connects to a higher voltage to a motor for a brief period. So in this case, let's say it's connected to the 25 volts. And this surge of voltage ensures the current rises quickly enough to maintain respectable torque and swift motor response. So this was bi-level drive. The next is constant current chopper drive, and this is also a sophisticated technique designed to deliver nearly the same current to the motor at all speed. So this consistency to provide the same current to the motor at all speed is important for maintaining torque and precision regardless of motors operating conditions. Now, one of the key advantages of this method is to regulate the motor current using pulse width modulation. So by modulating the width of the current pulse, the driver ensures that the motor receives a constant and optimal current level even as the speed varies. So stepper motor driver ICs and built-in pulse width modulation constant capability such as the Allegro A2919SB exemplify this approach basically. And these ICs, they integrate the advanced control features, allowing for seamless and efficient motor operation across a wide range of applications. And with constant current chopper drive, engineers, they can achieve reliable and consistent motor performance, which can lead to enhanced accuracy and great productivity in stepper motor system. So these were the 3 driving circuit, and this is the end of the lecture. Thank you so much for listening to me.